Okay, good morning. So welcome back to lecture vibration, and we continue to this part, the transformation of coordinate. So previously, you have learned decouple and couple on matrix M and matrix K. So if you can transform the coordinate to uh, initially couple means you can transform from the equation mh double dot plus kh equal to 0. Then you can transform to have diagonal matrix as a factor of h double dot plus, yes, some matrix here as a factor of h. This means initially initially decouple. Okay, so if it is initially uncoupled, then it is elastically coupled because here is still coupled. You can also do a certain transformation such that you can have from this equation you get still a not non-diagonal matrix as a factor of h double dot, and you have diagonal matrix as a factor of h, so you can elastically uncouple, but it's still initially coupled. Okay, but now a big question is posed: can we select coordinates so that both are uncoupled, which means you can transform in a certain way such that you can have diagonal matrix as a factor of h double dot. All right, because we are saying coordinate transformation, so it cannot be h again, but it should be other coordinates that has been transformed from h, right? And here also diagonal. Okay, something like that. So you have this kind of equation, it's easy to solve it. Let's say here is just call it a b c d. So we can easily solve this equation because we can have a y1 plus cy1 equal to 0. Sorry, y1 double dot. Here b y2 double dot plus dy2. So we can solve these two equations independently. That's why we really want to have uncoupled for both the factor of y double dot and y. I give you a hint before we get to see the whole thing. Uh, so from the equation to h double dot, no sorry, h double dot plus kh equal to 0. If you multiply both sides by inverse, right? So inverse time h double dot plus m inverse k times h equal to 0, because m is always a full rank matrix, so it has inverse. Then this become identity, and you have h double dot plus m inverse k h equal to 0. Then uh, we can apply, yeah, clearly we can see that this part is already identity 1 0 0 1, yet this factor is identity, so we can already have initially uncoupled. So we just need to um, transform this, okay, this matrix to be uncoupled. And the way that we can do is to use eigenvalue decomposition. So first, let's look at mk. Yeah, let's find eigenvalue. This yeah, eigenvalue decomposition of inverse k. So by definition, okay, let's call this what is matrix like this, calligraph. And by definition of eigenvalue, time eigenvector u equal to lambda time eigenvector u, right? And if you substitute this m by m inverse k times u equal to lambda m inverse, sorry, lambda time, yeah, lambda times u here, or you can write k times u equal to lambda times mu. So I get this because I multiply both sides by okay. So sometimes you can use this definition, or you can use this directly, okay. That's why in this lecture uh, you are given this term as the way you find eigenvalue, right? Yeah, here and here, yeah, here and here, okay. So k times u equal to lambda times mu. But this one, if you look at this, you find that this is not very obvious, um, corresponding to the definition. That's why I show this way, okay. Well, because M matrix and K matrix are symmetric. Yeah, actually M is diagonal, and K is symmetric. Then then inverse K is still symmetric, right? Because inverse, because is diagonal, inverse is just inverse of each diagonal. Um, let's see. Let's say k equal to A, B, B, C. So this is symmetric, and m equal to m inverse equal to 1 over m 0 0 1 over okay m1 m2 like this. Um, so inverse time k equal to uh, oh I think maybe I'm wrong. It's not symmetry unless one equal to two, right? So when I multiply by this, I have a over one, b over one, and here b over two, and c over two. So the matrix can be symmetric if one equal to two. So why uh, I'm interested in symmetric matrix? Yeah, because the eigenvector of symmetric matrix are orthogonal. So well, okay. So it seems that to have symmetric inverse k, we need to have specific case, which is to say one equal to two. But we can ignore that. Let's think about a general case. Um, but here we need the relation eigenvectors are orthogonal, which means this. Okay, eigenvectors um, eigenvector are orthogonal and model vectors are orthogonal, so we can have this relationship. Um, we choose u1 and u2 such way that uh, they are orthogonal, okay, so that we can have this relationship. And this one is called model vector because um, we don't call it eigenvector because k is not diagonal, okay. So we solve the algebraic problem from here. U1 and lambda 1 satisfy this definite this algebraic eigenvalue problem. U2 and lambda 2 also. Then um, we use transformation X equal to linear combination of Q1 and Q2. Sorry, combination of U1 and U2 by the factor of Q1 and Q2. Okay. because u1 and u2 are vector, we can also write like this. um, u1 and u2 and time q1 q2. So we transform from h1 h2 to be q1 and q2. Okay, so when we transform this like this, and yeah, because you want here, you this is kilometer, this is kilometer. That's why we can write down like this: u11 u21 and u12 u22 like this. Okay, and then we substitute h. Well, here I can also write h double dot. If I write h double dot, I have double dot here because u1 and u2 are constant, because they are eigenvalue and eigenvector and model, yeah, we call model vector, eigenvector and model vector obtained from matrix and matrix case, which are constant. So this matrix is constant. When you take time derivative on h, it means you take time derivative on q as well, right? So that's why we can substitute. Yes, so h double dot, yeah, here h double dot, h double dot here would be q double dot here, q double dot here. So you substitute this term, and h itself, is substituted into here, and finally you can reduce the equation to be uncoupled between q1 and q2. So you can solve these two equations independently, separately. Okay, so you can notice that there is a way that we can uncouple the equation, even though the dimension of the equation is higher. You can still do the same way, just use eigenvalue decomposition. Okay, let's see example from the equation. Yeah, h double dot, yeah, h double dot plus kh equal to 0 with initial condition. The initial position is here, and the initial velocity is 0. And then we solve the eigenvalue problem. So actually is uh, 0 0 like this. We use the same yeah, from the example that we learned before. I can recall it a little bit. Yeah, when we choose the same yeah, from which equation, yeah, From this equation, we choose this one 0 and m1 equal to m2 and k1 equal to k2, and we can reduce to a simple equation. Okay, so here are there is no complete equation, so yeah. Okay, I think we can get from here the m1 equal to m2 and k1 equal to k2. Okay, oops. Yeah, right here. So in here it's very it's summarized. So just to give you the process, after you have the equation and then you solve the eigenvalue problem, which is uh, um u1 equal to lambda 1 u1 and no k u1 equal to lambda 1 u1 and then k u2 equal to lambda 2 u2. Okay, we can have a two value of eigenvalue, and the first eigenvalue is this one and the second is this one, and here is eigenvector u1, this is eigenvector u2. Okay, u1 u2. After then we can have h as a linear combination of u1 and u2 by uh, q1 and q2. So we reduce the equation, the original equation, to be uncoupled equation like this, and then we solve for q1 and q2. Okay, um, because the characteristic equation has purely complex number, then the homogeneous solution becomes cosine like this. Then finally we have the final solution for it, which is combination of q1 and q2, u1 and u2 by q1 and q2 like this. So the same as solution that was solved before here. Yeah, same as solution here. Okay, so next time I will have a whole process. Yeah, I will require you to follow all the process practically on using MATLAB to find eigenvalue on this example or others example. But for today, I will only go on the with the slide. Okay, so the big idea is just to find a way that you can transform the original equation to be uncoupled equation, this one, so that you can analytically solve it easily. Okay, quite different. Oh, its response is much slower. Oh, I see. So it will be confusing, I guess. All right. The next part is respond to harmonic force. So in the previous part, we only consider the right hand side as a constant, right? So the oscillation depends on whether we have the damper or not. If we don't have damper, then the solution oscillate, right? But if we have the input force is harmonic, which means it is a trigonometric function. So this term is represent trigonometric function because it combine between cosine and sine. Then you always have oscillation solution, specifically on the particular solution, right? So in order to analyze this system, this equation, we use uh, Fourier transform or another equivalent method. Actually, this is just like a Fourier transform. Um, well, so here we can see that if the right hand side is trigonometric function, e to the I omega t. Yeah, this is exponential, but because the exponent is complex number, then it become trigonometric function. So either the right hand side is trigonometric function, then the left hand side h and the derivative, the first derivative and second derivative are supposed to be trigonometric function as well. That's why we can assume that the solution h must be some coefficient or magnitude times trigonometric function. Okay. Then we can take the first time derivative and then take the second time derivative and substitute back to this equation. Because when you take time first time derivative and second time derivative, the difference between uh, yeah, difference between these two first time derivative only the factor of I omega. So here is I omega, and then you take the time derivative again, you have another I omega. So I omega times I omega, you can have I square, which is minus 1, and then omega square. That's why you have minus omega square here. Then you have this equation. Um, the coefficient of H here is called impedance matrix in function of omega. So to find H here, you can multiply impedance inverse. So impedance inverse time impedance become identity here. Then you only have impedance inverse time the input force here. So this is the impedance inverse represented by this kind of matrix. If you have 2 by 2 matrix, you have Z11, Z12, Z21, Z22 like this. Then you find the inverse. The inverse of this matrix by formulation is 1 over determinant times the transpose of cofactor matrix. Okay. So all of this is C inverse. If you apply Fourier transform, yeah, you can have the same thing. Or another way, first you use Laplace transform, but after then you substitute S by I omega into the transfer function, and that transfer function with the I omega is called the impedance matrix here. Same thing, okay? Yeah. I can briefly show you. If you apply Laplace transform, because I think you already learned Laplace transform last semester. If you apply Laplace transform here, you can have s square plus cs plus k like this, and time h of s, right? So in here, if you call it as z of s, right, you can call it that way. And after that, you just substitute s by I omega for harmonic response. Yeah, for harmonic response, you just substitute s by I omega. That's it. Now let's look at a special case undamped system. We don't have the matrix C, okay, zero damping matrix, and the entry of Z11 is this. From the previous lecture, you already saw it, and yeah, Z22, Z12, and this impedance matrix is symmetric. Then you can compute this because you already have all the element inside this matrix, and then you multiply it by f1 and f2, then you have h1 and h2. Okay. Yeah, to easily analyze this, let's take k1 equal to k2 and m1 equal to m2. Then h1 and h2 will reduce to this. So the interesting part is the denominator. You can see that, yeah, this one is natural frequency one, natural frequency. I think yeah, this one and this one, natural frequency. And you can see that if the frequency of the input force approach to the natural frequency, then the amplitude increase, right? This is called resonant. Yeah, you have seen it when we uh, analyze the 1 degree of freedom, okay? Same thing. But for 2 degree of freedom, your system has two natural frequency. So when you have four with frequency approach to any of the natural frequency, you have the resonant. And in this case, resonant is bad because the amplitude of vibration grow. So this curve represent relationship between H1 and the frequency of the input force. Okay? You can see here, if the frequency approach to omega 1, then amplitude h can be very large. So if approach from the left hand, from the left hand side, amplitude H grow to infinity. But if you approach it from the right hand side, the amplitude H grow to minus infinity. So this is just a fractional function. Yeah, because fractional function in terms of omega can easily draw this kind of curve. Yeah, this is just a note. Denominator originally minus minus, and then plus me. It means if omega smaller than omega one, which is also smaller than omega two, is negative negative. Then the amplitude h1 and h2 are positive for this part. So you can analyze simply this way. And yeah, on the note number two about the phase between H1 and H2, and H1 for H1 this part and this part, H2 from for omega during this zone, H1 and H2 on the same phase, which is 0 and 1. Okay, this part and this part, H1 H2 has the same phase. So the phase 0, phase angle 0, and this one with this one, H1 and H2 in opposite phase, so 180 degree, something like that. Okay, so that's all for the undamped system of 2 degree of freedom. You have any question?